Hi again, my name is Bruno, and I'm going to talk about the object code emission and LLVM, and LLVM-mc, which is a new and experimental tool to handle object code right now. So I'll talk a little bit about the motivation. Why do we want to direct emit object code? I'll talk a little bit about the background, how the code emission is done today in LLVM. And then I'll explain in the actual code emission what is our currently design. And then using this, I will show you how I implemented the object code emission for ELF, and what are the current limitations for this, and the new tool, LLVM-mc, which addresses the previous limitation we had. So we have the Nonpath we usually do in compiler. We use our compiler to compile our high-level language, and we generate a .s, which we use as an input to assembler. And then the assembler get us the final .o file, which is used as input to the linker, which will give us the final executable. We want to cut that down and embed the assembler into the compiler, so the compiler can just generate the .o directly, and we just send it to the linker and get the final executable. So why direct object code emission? First, we want to bypass an external assembler, and the reason for this is that we want to speed up compile time. Now a little bit of the background. We have the emitters now in LLVM are represented in two ways. We have the assembly printers, which actually emit .s stuff, and we have the JIT engine, which emit blobs of bytes to memory and run from there. So the assembly printer we have instructions that are described in RLTD files. Anton talked about that in his talk earlier. And in these TD files describing the instructions, we have like a lot of auto-generated code. And it's likely that we can use then those generated methods to print the stuff automatically. So here is a little sketch of how it's done. For example, for the x86 assembly printer, when you're printing an instruction, we only choose, if the assembler dialect is something like Intel or AT&T, we just call the auto-generated methods for printing an instruction. Now I will show you how the JIT works. JIT works basically emitting binary code to memory. We have blobs of code which are emitted by a target-specific emitter. So this target-specific emitter gets the encoding of instruction and emits to the memory. And this code is emitted as a per function basis. So we have like a machine function pass, which we'll call for each function will emit the code to the memory. And we have different, for each target we have a custom emitter. For x86 we have one emitter, for PPC we have a different emitter. So for example, the only one of those emitters which are actually automatically generated is the PPC one. The x86 and the ARM one are written by hand. So here we have a regular emitter for JIT. And then we have like this method which is emit instruction, which will effectively emit the encoding and the instruction itself to memory. And this is done through the machine code emitter. So first we have the emitters. We have backend target-specific emitters like x86 emitters, PPC emitter. And each one of these emitters will have something like this emit instruction method, which will be implemented different for each target. So for example, suppose we want to emit an opcode prefix for a lock expression that is locked in x86. We can just like call this machine code emitter MCE emit byte, and it will throw that byte into the memory. So this is what it does. This MCE interface I'm showing here, it's a generic one and can be specialized to emit the code in the way you want. So for example, the JIT does a specialization of the machine code emitter, which is called JIT code emitter. And it implements a lot of methods to actually write those bytes to memory. So we have simple methods to emit byte, emit different words depending on the engine of the target, emit alignment, emit stuff for dwarf, debug, info. So when you try to, the first time we try to implement object code emission in LLVM, we try to use the same scheme as JIT does. So we actually inherited from the machine code emitter class and implemented the object code emitter class. That way, when you call the MCE I showed before, instead of dumping bytes to memory, it will write to an actual file of a specific format. So for example, here's how we do it. We have a generic object code emitter, and you just specialize it to be ELF code emitter, a COF code emitter, or a match-O code emitter. And when you're using when you're in JIT, the MCE just write through the memory directly. But when you're using object code, we create an abstraction called binary objects, which are basically high-level representations of sections and segments. So we have a lot of binary objects through the code, each one for a different section. So for example, we have the ELF code emitter. And in the ELF code emitter, we have to handle something, we have to render stuff that it's not, it's format specific. So for example, for ELF, since ELF and match-O, for example, doesn't have the same section names for where to put the constant pools and jump tables, we have to handle this specifically on the code emitter. So we do special handling for constant pools and jump tables on the ELF code emitter. And we also handle the target generic relocation codes to the format specific one. This example, we have a reloc absolute word for x86, which is a generic and can be used in match-O and COF and ELF, and we map it to the num for the ELF one. So this is a little sketch on how this is all done. We have the code gen here, LLVM-IR, and after code gen, that function emit instruction I showed, we start to encode an instruction called the MCE emit byte, and it will call the ELF code emitter emit byte. And if you are actually emit code, the actual binary object representing in the moment will be a .text, for example. It can be other, but usually a .text, and you call the binary object emit byte, and that will hold the byte for that section. So we have the ELF code emitter, which will handle those specific stuff for ELF, and we have after we're done with the ELF code emitter to emit code, we have to handle all the stuff that is specific to the ELF format. For example, we emit the symbol table, the string table, the header, and the relocations into its own section, and then we dump the binary object to a final file. But okay, this works, this is great, but actually it doesn't work because of inline assembly. When you hit the case of inline assembly, we just don't have nothing to do because it's in a different part. It's emitting object code, and the assembly stuff, it's in another part of the code. So we have to have an assembly parser. So that's why the new tool of LLVM-mc. Okay, what's LLVM-mc? It's actually the machine code driver. We are using it actually to be a playground with the machine code stuff. We use it to we are writing an assembly parser, a disassembler, and assembler, and we are using the LLVM-mc to drive all the commands for these guys. So our goal with the LLVM-mc, we want to auto-generate everything. That means we want to extract all information from the TD files, and with that, we want to be able to auto-generate the assembler, the assembly parser, the code generator, and everything here. Actually, in the future, the assembly printer stuff. And we want to integrate the assembler into the compiler so we can have that path I showed in the beginning. So we hope you can beat at least 20% speed up at -0 and -g. And we hope you can share binary iter's code base as much as possible. So if someone wants to add a new format or a custom format, he doesn't have to hack too much in the code base. So this is what we have in progress right now. We have, for those who are actually working on an assembly for a specific assembly language or something like that, you can use the -a/x to debug the production of the ASM parser. So you can have here, for a simple data section with hello string, you can have an identifier, you can see the string there. It's really useful for debugging. We can actually parse and assemble .s files. And from this parsed.s file, from the representation we have, we can actually emit again the assembly file or object code. And we can actually emit the assembly file again in a different syntax. So for example, for x86, we can parse Intel ASM file and dump an ATT assembly file. So this is just an example of this working. We can assemble from the input for an .s file and like show the encoding for the instructions. We also have in progress a completed assembler, which includes the relaxation phrase, allowing like later optimizations. That is true, for example, in x86. After the relaxation part, we can know if we can, instead of using a long jump, we can use a short jump, for example, doing small optimizations for code size. We have more stuff we're actually working on, like an interactive disassembler. This should make really easier to write regression tests for new instructions. For example, you just call LLVM-mc minus disassembler. It waits for input, and you just write the bytes of the instruction. It will output you the actual mnemonics for it. This is really cool because we won't need like to have stuff in ELF or match-o. We just can write the instruction itself, have the dump for it, and write automatic tests to see if we are encoding stuff right. So I'm talking about the architecture of this LLVM-mc, how it's done now. So we have an assembly parser who emits codes through an MCWriter. And this streamer can be specialized to emit assembly or object code, as I show you. So here is how does it work now. We have .s file as input. We call the ASM parser for it. Suppose you want to emit an .o directly. It will call the MCWriter, which will call emit instruction. We will encode instruction. You do that a lot of times until for the whole function. Then we call the match-o object writer to finally write into the file through the write object. If instead of this we want to output the .s again, we use the MCWriter, which will just dump into the right dialect we want. As I showed before, you can like input AT&T and like output Intel syntax. Since it's really new, this LLVM-mc, the current limitations for it is that it's quite experimental and demands a lot of code refactoring and cleanup because we want to share as much as code as possible between the assembly printers, the JIT, the object code emitters, and right now it's hard-coded for match-o. So the Emission, which was implemented in that on that scheme I showed earlier, it's not integrated into the LLVM-mc architecture, and also the assembly part, the specific bits of ELF assembly are not implemented too. So it should be straightforward to implement those, but they are not there yet. And the assembly printer is not entirely converted to use the MCWriter right now. We just have that for x86, but it's not in the shape we want so far. Okay, so the MCWriter future, we want to support other binary formats, and we want that to be really easy to do for a new format. We want the MCWriter to have a lot of new specializations, like for JIT, for dwarf, exception handling, for debug info. We don't want, because if we're working on that, like the actual way that ELF is emitted, we are like duplicating a lot of code. So it's better we have specializations for this guy and share as much as code base as possible. Eventually, in a moment, the JIT and the ASM printers will share the same code base, which is not done yet. And it could also, if we achieve like the 20% we want, we won't care more. We won't have any reason to care about compile time with -s, for example. You can use -s to generate by default some kind of verbose assembly, which will help a lot in debugging assembly code, generated for new backends and stuff like that. And code can put a lot of stuff in this verbose assembly. For example, information about loop depth, about encoding. This really helps while debugging backends. So the future design we want, it's like, for example, for printing.s, we want the code gen to call the emitter, the code emitter. The code emitter just called the MCWriter, and since we have an implementation for outputting again .s, like MCWriter, it will be done. For JIT, the same thing. They will eventually share the same code emitter. So actually, until the calling MCWriter will build the same code, and you'll just, since MCGTstreamer will be implemented, you'll dump the bits to the memory. For object file emission, like for .o writing, we can have again the same scheme. We go through the MCWriter. We have a new implementation like MCObjectstreamer. We call the assembler backend, which is part now of the LLVM-mc, and it output for us a .o. In the case we had our previous limitation, now it's resolved because we can call again the MCObjectstreamer, but we'll call the assembly parser for the inline assembly stuff. And that will call the MCWriter again and use the same interface to call the assembler backend and finally emit the .o. So, and this assembler backend will be something like this. We'll provide the relaxation, and then we just call a generic MCWriter. We'll dispatch things through the MCWriter, for example, or the LLVM and to a final .o. And that is all.